HTS Josephson junctions and are dead end or new opportunity in their development. Thank you.
Thank you very much. I would like to thank the organizers for this kind of invitation. I think it's a good opportunity to combine somehow the knowledge of superconducting electronics and nano and materials, because there is a certain difficulty, I think this is well known, with the HTS junctions. The beginning, we thought, or people thought, that one can very quickly make thousands, 100,000 or more of these junctions, just like for the low TC material, but that doesn't seem to be the case. So what I would like to do is talk about the opportunities, research opportunities, which are in these junction developments. On the other hand, the question, is it really something which we can reach, and what are ways to go there? So in order to do this, I had contact with a lot of people on it around about the last year. We had a discussion on this also just during the symposium on 20 years high TC superconductivity in Zurich. And I think what hopefully will evolve is a program which goes back more to the fundamental research and to nanotechnology in order to solve some of the essential problems of this ITC junction dilemma. An important part with is also just here the Fluxonics group. It is a European network which I chair for superconducting electronic devices where all major laboratories are involved, and we intend there also just to focus, apart from classical superelectronics, on these ITC questions. So what I'm going to do is just short prelude about superconducting electronics. I don't have to say much about it, just to show you just in reading a little bit of it. Then let's have a look at what is going on, or what was going on with ITC junctions and what is going on now. Then something about these yttrium barium copper oxide gold niobium junctions as an example that there are ways out of the difficulties, and try to identify what have we to do just in future. So why digital high TC superconducting electronics at all? If we can do everything with low TC, why should we use high TC at all? As you heard already, 77 Kelvin is not just a question, it's 40 Kelvin. Cooling to 40 Kelvin would be no problem. Superconducting electronics at all means here in this graph, delay time per gate, and here the energy to charge a gate, that RSFQ is very nicely located with a very short delay time and a reasonable energy to charge a gate, not far away from KTR or room temperature, being moved slowly to this direction, but I think already it's good enough for most applications. Also, someone just gave a very nice talk on just the essence of superconducting electronics in one of the workshops last year. And if you look into the power consumption per gate and the speed again, you see compared to these semiconductors, we lie very nicely just here with SQ in a low energy and high operation speed area. So what is the big difference between HTS systems and low TC systems? It can be operated with small cryo coolers. It is suitable for a small scale system where we don't need huge numbers of junctions, but fast. Competitors are conventional low-end systems such as high-speed measurement systems. And the same for the LTS system, suitable for large systems. Competitors are conventional high-end systems, and larger the system becomes, such as supercomputers, the better the performance. This is ISTEC opinion, and also some, but also the opinion just in the European community, and I think it's the same just also in our colleagues in the USA. What does it mean, just their small systems? If one puts in 1 watt, or needs 1 watt of cooling power in the code, for 4.2 Kelvin here, one has to apply some kilowatt of electrical power in order to cool it. If we go, for instance, here to the temperature of 40 Kelvin, it's down to, say, of the order something of 100 watt. So it's the power consumption which you also have in your PC. So it's acceptable. You can make for instance, a rack-mounted system or a tabletop system which is cool to this temperature. Those coolers are in the meantime available, very reliable for many years, very quiet. And also there are developments to make coolers that are integrated already in a chip and can be operated just with pressurized gas. So there is no reason from the cooling side not to use circuits, for instance, at 40 Kelvin or up to 70 Kelvin. Compared to low TC, high TC has also the speed advantage. If you look here into the critical current density plot, and ICRN just here related to the gap speed of this thing, and what you need for the circuits. You can only use non-hysteretic junctions for the RSFQ calculations, and that means you have to shunt tunnel junctions to make them non-hysteretic. High TC junctions are inherently non-hysteretic, so you get quite some speed advantage with the HDS junctions compared to the LTS junctions. So that means for the clock frequency, for the high TC, we can actually, if funding would be good, just achieve, I think, quite quickly very high operating frequencies. And we've shown this in the past, just here with a simple modulator for the for sigma delta and quanticizer. And all these circuits operated very easily and quickly, already up to clock rates up to 170 gigahertz. So it's possible, low complexity circuits in high TC technology to make it. But if you try to make large numbers of junctions, you fall in the trap, and I will come to that later. So let's have a quick run to high TC Josephson junction, how that actually started. And before that started, we had no high TC at the time, or better, the high TC at that time was not the oxide materials, but it was niobium tin, it was niobium germanium. At the time, McBeasley at Stanford, with my group in Eastern Germany, tried to make devices, Josephson junctions and devices based on these two materials. Both are characterized by a very small coherence length. We both did not succeed in making tunnel junctions. We both just concluded at that time in the meeting as long as the materials development is not in a higher state, there will be no tunnel junctions only because of these very small coherence lengths materials, the interface is dominating the characteristics. And that means interdiffusion, all these mechanisms actually will destroy it. And we just had two ways. In East we used then microbridges, and in Stanford we used just a step here in order to make such a junction with the overlap of gold, so proximity effect junction. It worked in both cases, but no tunnel junctions.